Hello, everyone. Welcome to today's presentation. This is the third and final presentation of the AEC Coffee Break Series, focusing on dynamic analysis. And today's focus is on time history analysis. We're going to talk about some different applications we see our users using SView for this type of analysis. We're going to talk about one of the nuances of time history analysis, time step size, and how you can use that to your advantage, but how it can also be to your detriment if you're not paying close attention to the values that you're using. Time history analysis also has some unique aspects of post-processing that are helpful to understand. And there are two different ways to integrate the time steps as well that we'll get into as well. And Andres, who's going to be joining us today in the demo portion, is going to talk a little bit more about some of these topics in the demo at the end of the presentation. So let's jump into this now. Here we've got a bit of a discussion on the different types of applications we have for time history analysis. And a few of the obvious ones that come to mind, well, the one obvious one that comes to mind immediately is earthquakes, since we've talked about that in the previous session on response spectrum analysis. And we can do that with time history analysis. We have the ability to support ground motion or multi-support ground motion, in this case of perhaps different ground motions on the same model. Maybe you have a long span bridge, for example. We have machine vibration, so where you have a harmonic load that might be described with a sine curve or some other type of polynomial function, perhaps unbalanced motor motion. We also have blast or impact analysis, where we're kind of simplifying the impact loads to a curve that can be described in SView. Obviously, Altair does have other tools like Radios to run explicit nonlinear analysis as well, if that's something that you're interested in. And we may want to consider damping during these as well. So that's something that we need to think about when we're running these analysis. If we do have some sort of initial load, for example, is there damping in the structure that is going to basically drown out that oscillation over time so we don't get steady state response during the entire initial loading response. And as you can see here, I've got a little video that I played at the beginning. This is actually just a unique example of using time history loading and analysis. In this case here, we had a pendulum model, which we were basically pushing to the side and holding it there. There was a bit of oscillation, and then we let it go and watch it swing. This is just a quick snippet from SView to see how that looks. Now, it's important to understand as well that time history loading and the analysis itself must be broken into discrete time steps, and that's something that we're going to be talking about. So time step size is obviously very important. And to understand the time step size, we have to understand essentially how frequently we want to sample the response of the structure. And I've done my best to kind of illustrate this with a very crude drawing, as you can see, a very colorful but crude drawing. So at the top, I have what we'll consider the true dynamic response of our structure to some sort of oscillating load. Maybe it's just some sort of steady state response, we'll say in this example. And in the bottom half of this image, I've got essentially just a couple different lines that are connecting dots with different time step sizes to sample this response. So as you can see here, the green line, if it weren't obvious from the plot, has the coarsest time step size, meaning that the time steps are furthest apart, and those increments that we sample those time step sizes, we'll get more into how they can vary or not vary depending on the type of time step integration we use. But in this case here, we're assuming we have a fixed increment between each time step. So we won't necessarily be able to guarantee that we're going to get every peak or trough of our response located exactly on that increment or the discrete location where our time step lands. As you can see here for this green line with the coarsest time step size, we land just to the left of the trough here, and in the next time step we land just to the right of it. We just so happen to land right at the peak for this this next plot here, as you can see, or this next peak. And as we go along, we're starting to see that the green line, if we just isolate that and compare it to the black line, it does kind of look like the black line, at least following a general trend. But if we were concerned about the maximums and minimums in this particular plot, we might have some issues because we're not necessarily capturing those. And as you can see, when we use finer time step increments, smaller time step increments, we can do a better job of capturing the true shape of the curve, but we're still missing out on some important details. And this is assuming a fairly regular, and in this case, I would say fairly long period response. Now, to understand what type of time step we want to use, it's important that we understand the frequency of loading that we have. If it's a harmonic function, we probably know what that frequency is, especially if it's a fairly, like a sine wave function, for example. We also understand the mode of vibrations of our structure. So if the structure has a tendency to oscillate at a certain frequency, we want to make sure that we're able to capture that with our time step. So we don't want to have one time step for every single period of vibration. We want to have much more than that to capture the true vibration. And it's important that we do that to capture the higher frequency behavior. But there's always a balance. We want to be able to obviously capture the important aspects of the analysis, but there is a kind of a tipping point where we're not getting much more return for an increase in analysis duration and computation time. Obviously, modern computers have come a long ways, and running a time history analysis isn't something that will necessarily take a week to do, but it's something that does take longer than your typical static analysis. So SView uses a numeric time step integration method for solving each time step. That's why it is important for the time step size to be sized correctly in order to get an accurate solution. And again, if your time step size is too large, the loading events might be missed, and the components of the structure's response with high frequency may be misinterpreted, or you might get inaccurate results due to that. And again, if the time step size is too small, the analysis is going to take too long. The results files will be large and perhaps more difficult to work with. So what we found is if we just look at seismic analysis, it's generally accepted to focus on the low modes of vibration and hence use a relatively large time step size compared to other types of dynamic loads that we might have. For example, machine vibration and blasts or explosions, which will require a much smaller time step size. This is all relative. Obviously, as you'll see in the demo, the time step size we use will be quite small regardless. So after we've run the analysis and we've selected accurate or even inaccurate time step sizes, we want to understand how we actually interpret these results and look at everything that we've calculated. So we have a parent load case that describes the time history curve, but underneath that parent load case, we have a number of different child load cases for each time step as its own isolated load case. So we can review envelopes of the entire structure or a specific joint or member for the time history load at each time step or individual points time steps in isolation. And all this result data is presented to us in a numerical format as well. So that just lends itself nicely to, if you want to do any additional post-processing, it's very easy to grab that data and massage it and crunch it in any way you like. And as you saw in previous presentations as well, time history analysis is a really good application for SView. Its rendering capabilities are stronger than S-frames, so you'll be able to look at basically the response of your structure to these loads. And if you had, for example, a time history response with contours like this one here, you'll be able to actually see the contours changing as you go throughout. I've excluded the legend from this, but this will help you identify where the hotspots might occur, when they occur in the response as well. The last topic I'm going to jump into here before we move on to Andreas's demo is the time step integration. And essentially in SView, we have two different options. We have a constant time step integration, which we kind of introduced in one of the earlier slides, where we specify the number of time steps we have and the increment between each time step. And this is very reliant on you as the user to select a reasonable time step size. Now, you guys are engineers. I'm assuming most of you have experience or will have some sort of research involved in your selection. And our training courses on this topic can certainly help with that as well. But it is fairly dependent on your input there. So it will use that same time step size for the duration of the analysis. And here's an example where let's just assume that we had 0.01 second increments between each one of these y-axis grid lines. And if we selected a time step size of 0.005, so basically we land at each grid line and halfway in between, we can interpolate those points, and you can see here that the green line is looking a little bit different than the red line, which would represent the true response of our structure to this loading. So it ends up giving us perhaps not a very clear picture of what's going on. We're missing some of the peaks, some of the troughs, and it's purely chance that we land on some of these points with this even increment that we have. Not to say that it's not a good approach, but it does require you to understand what type of time step to use. That's in contrast to the variable time step integration, where you specify initial time step size, a minimum time step size, a maximum time step size. So you basically give it a starting point and then a window of time step sizes it can use, and a critical jerk, basically the change of acceleration that will be the threshold for what the solver requires a new time step size for. And then you specify how long you want the analysis to be sampled for. And then the solver is going to sample the response during times where you have rapid changes in acceleration that meet this critical jerk requirement. And we find that this uses on average about 30% less time steps for the same level of accuracy. Here's an example again, assuming that this is an acceleration plot. Anywhere where we have a change in this slope, we're going to get some critical jerk threshold being met. Again, that's dependent on what threshold we use, but the defaults are usually pretty good as a starting point. And so it's going to do a much better job of getting these peaks and troughs. And it's also not going to need to sample as many redundant points where we have essentially a straight line between our joints. So that's where the computational efficiency comes in when we're doing this sort of thing. So at this point, I'm going to open up the floor for Andres to do his demo of S-frames time history analysis. So Andres, I'm just going to make you the presenter if you just give me 1 second to transfer control over.
Thank you very much, Matt. And well, hello everyone. If you've joined us during the last couple of sessions for this webinar, you might recognize my voice already, but if not, my name is Andres, and I will be happy to run a demo for you to show you the different ways the time history analysis can be executed in S-frame. So I have this model ready over here. It's a steel building with some bracing and concrete slabs modeled as shells for some context. But I'm going to be more interested in the loads now. So why don't we go to the loads window? As you can see from the drop-down menu, we have a total of 4 load cases defined already. But this one over here, the ground motion in X load case, is a time history load case that we defined beforehand. So I'm just going to select it, and we will be focusing on this direction only for this presentation, meaning the X direction. But of course, this procedure can be applicable to the remaining directions too. So now that I've chosen it from the drop-down menu, I can go to the time history tool over here, right-click on it. This will show me a new dialog popping up on my main screen. And I can see that we have an accelerogram defined already. It's for the Loma Prieta earthquake that occurred in the Santa Cruz Mountains in California back in 1989. And this is simply a record of the ground motion during the seismic event. And it's showing us the acceleration variations throughout the earthquake's duration, which was about 40 seconds. And in this point, it's important to mention that S-frame comes with a default database of ground motion records, which is where I took this ground motion from, but it is also possible to define your own if you wish so. So for more context here, our dynamic load type will be a support excitation type, which means that the supports are going to be shaking in the X direction with the excitation shown on screen, which is this one. Once again, as we're focusing on the X direction only, my scale factor will be 1 and the rest will be set to 0. So let me just close this guy over here. I didn't make any changes. Let's go now to the analysis menu over here. Let's check my configurations for the linear dynamic time history analysis I have already run on this model. We first went for the constant time step integration method, and I have selected a time step size of 0.005 seconds and a total of 2000 time steps, which doesn't necessarily account for the earthquake's total duration of 40 seconds that we just mentioned, but we try to keep this one simple for the sake of time in this presentation. As this analysis will take some time to solve, we have already solved it to show you the results. So in this regard, please bear in mind that the smaller the time step size is and the larger the number of total steps are defined, the more time the solver will take to finalize the analysis. Hence, we didn't want to wait too much while we presented this. If we wanted to cover the full earthquake's duration, we could have entered a time step of, for example, 0.005 seconds and 8,000 time steps, for example, and that would certainly take a whole while to solve. That's why we're not going to do it for the time being. But just for your information, the current settings took us about 22 minutes to solve this model. So if you were to do this on your end and you were to take a look at the solver's output during the analysis, you will notice that in some cases, well, first of all, you will notice that it solves the static load cases first, in case there are any, and then it solves the time steps for the dynamic load case, which in this case would be load case number 4. Each time step is equal to a load case, hence the lengthy process. And in some cases, you might receive some FYI messages in SPring that we will be reviewing in just a second when running this analysis. For example, DE018 or DE021 FYI messages, sorry, which you shouldn't worry too much about. We will be explaining this in more detail in a bit. The first one is only going to be problematic if there were any initial loading conditions that are causing a lot of changes in the structure right away when we start the analysis and the vibration. And the second one would only be telling us that our initial conditions are 0, meaning, for example, that our structure was not moving already once the seismic event started happening. So I'm just going to click on cancel here. I don't want to click on OK because we will take 23 minutes to solve this guy. And now I can go to the graphical results window. Let me just untoggle this guy. Oh, well, let me just show you what Matt was talking to you guys about regarding the creation of load cases. I will now see that I have my original time history load case, which is this one, ground motion in X. I will not click on it. I will be very careful not to do it, because if I were to select it, it would be creating an envelope of the results for all the child load cases, which are in total 2,000, because I am selecting the parent load case. But I will not do it for the sake of time, because I just did it 1 second. I did it 1 second ago, and the program went kind of crazy. So that's not something we want to do for the time being. As we can see down here, we have a series of child load cases underneath the parent load case. Each one represents one of the steps. As we can see, we have 2,000 steps, sorry. Let me just go back here. And I can choose any of these, for example, step 1. And I can show the deflections, which is what I'm showing here. It's kind of scrambled, but I'm showcasing my deflections in the X direction, which is the direction of interest. And we will see our numerical results by toggling this option over here. I can click, for example, on any joint. I will right click on it. Let's go for this guy up here and click on response time history. This will pop up a new message or a new dialog over here. And I will first see the input ground motion, which is the accelerogram that we defined initially. But I can also click on the time history response tab, which is this one over here, and see the joint's response during the time history analysis. I can show the acceleration variations, which is this case right here. But I could also be seeing the velocity variations or the displacement variations over the total of 10 seconds that we defined with our time step size and our number of time steps. As we can see, it is displacing about 9 millimeters in the positive direction and about 12 millimeters in the negative X direction. And We can also check all this information through the numerical results window to corroborate the received results, but I'm not going to lie, it is not very eye-catching or illuminating for our purpose at this time, so I'll skip that part today. Just gonna close this guy over here. And as Matt was mentioning before, we also have SView, and it is integrated with S-Frame, and I can actually run it from this menu here in SView. But for the sake of time, I have already done this, and this is my model over here. I have, as you can see, my analysis has been run already, and SView is open, and I could have picked, if I were to do this for the first time around, I could have picked only my load case of interest over here, and maybe pick the object contours to better visualize this. And once I am done, I can simply click on the play button over here, and it will start to run the animation. You will be seeing down here the variation in acceleration in the 10 seconds that we defined for our analysis for this time. Now, let me just pause this guy over here. On the other hand, we have the variable time step integration method that we mentioned before. So to show you the process, this is my second model over here. It's pretty much a copy of the first one. It's exactly the same. So I will go straight into the run analysis menu over here. And I will show you the different variables we can define for this method. I will have my initial time step size defined as 0.001 seconds to make sure that the first time step is not too large, and to also better capture any changes happening during the earthquake. I'll leave the minimum and maximum step sizes as we have them over here, and I'll also be leaving my critical jerk as it is right now, and I will define my final time as 8 seconds for this one, which is already done. So once I click on OK, this will start solving our model. Let me just drag this guy over here so you can see it more clearly. This is now starting to solve. This is live for your information, as you can see. So we're just going to see how much it takes for this guy to solve, and we will be comparing that duration with our first example, as well as the results that should be pretty much similar. You will notice how the time steps will cease to be generated much earlier this time. We won't be reaching 2000 by any means, as we explained it before. We won't be looking at a defined number of constant time steps, but S-Frame will be looking for the variations in acceleration to plot a more accurate curve, like the one we showed right before the demo started. So,
and maybe just to add, sorry, Andres, maybe just to add a point while we're waiting for this, the possibility that the constant time step integration had missed one of the peaks or troughs is obviously lessened, or at least mitigated when we use more time steps in smaller time step increments. But this approach will actually make sure that we hit those. So it is possible that the peaks and troughs could vary between the two of them. You can go ahead now, Andres, just want to add that point.
Thank you very much for adding that up, Matt. It was an important thing to mention. And once the analysis is done, as we can see, this time it only took about 1 minute, maybe a little bit more than 1 minute. And you will see the two messages I mentioned before, DE018 and DE021, which we shouldn't worry too much about. And we are getting additionally another FYI message related to our maximum time step changes. So what we might be looking to change that value in the future, but for the time being, we won't be doing it right now, as it's not entirely relevant. So I'm just going to hit any key on my keyboard, and let's wait for this guy to load. Okay, we are taking back to the graphical results window again, and I can do the same exercise to check our time history response by right-clicking on Well, first, I can select any of the desired time steps. In this case, I will go for this one because I think it's kind of more similar to the one we showed before. I'm going to click on this same guy over here and click on response time history. And we can start reviewing our accelerations first. If you remember the first example, we can see that the second method is producing a very similar behavior as it was expected, but this time the acceleration peaks are being represented with more accuracy this time, and we can see that the peaks are spreading out more evenly as opposed to the first model, in which we saw much more abrupt peaks given by the first method's approach. We can actually, let's go back to this guy and just compare very quickly. You will immediately see that these are peaking and they are like less distributed. They are lasting 10 seconds. It's a bit more, but the peaks are kind of more exaggerated in this first model as compared to the second model over here. And the same applies, for example, if we check the displacements, they're going to be a little bit more well represented in this case for our variable time step method. And finally, I'm just going to close this guy over here, and I'm going to go to SView once again. So this is the same approach. I'm going to select my load case over here, show my objects, and I can now run an animation for the 8 seconds that we defined for this model. This will help us to better visualize the dynamic behavior, and this is what we had prepared for this session in terms of the demo, and we hope that these two brief examples helped to better explain how the different time history analysis methods can help the user to represent a more realistic behavior of their structures and run more efficient analysis to better capture the high frequency behavior and use the results provided by the solver to design safer structures. Thank you for your attention, and back to you, Matt.
Thank you, Andres. You know, from a high level, really what we saw here is that unlike the other types of analysis that we ran in this webinar series, this actually allows us to not only look at the response of our structure to some sort of dynamic or looking at the dynamic behaviors of our structure, but also looks at the response to time varying loads rather than the static loads, for example, that we applied during an RSA or equivalent static or lateral force procedure. And we have a lot of control over the parameters to change the accuracy or the performance. And that is something that does kind of fall on the engineer to make sure that this is in line with your expectations and your needs. So with that, I'd like to thank everybody for their time. I hope you enjoyed this series on dynamic analysis in SRAM.